Okay. Just hide detail. So is that screen showing okay for you, Jay?
Yes.
Okay, fantastic. Thank you very much again for the kind introduction. I am going to give a presentation today about some of the work that we do in my group here in Australia. And the work that I'm going to talk about today is about really connecting mathematical models with real-world data and trying to think about how we can learn about problems by this working at this interface really of mathematical modeling, computer modeling, and data. So I'm going to talk about, as the title in the abstract suggests, prediction, estimation, and identifiability with mechanistic models. So the model that I have given different types of talks related to this theme over at different times. And what I'm going to try and do today is talk about an extremely simple mathematical model, perhaps the kind of model that you might have had exposure to in first year calculus or in maybe even in high school. But what I'm going to try and impress upon you, it's really the connection between the model and the data that I'm interested in. And what I'm going to talk about today can be applied to more complicated models. So sometimes I've given a talk like this and some audience members really want to ask questions about the models, which is fantastic. But I'm trying to make a connection between models and data. So I'm going to work with a very, very simple model. That doesn't mean that the applications of the model are not important. As I'm going to try and point out, they're very important. So I've got some figures on the screen here. I'm going to come back and talk about these in a moment. But before I get started, there we go, slides going well. The work that I'm going to talk about today is work that I've done with a number of people, including graduate students and undergraduate students. And so there's several collaborators, but what I really want to do is just highlight the main collaborator. And the main collaborator in this work is Oliver McLaren. Oliver is someone who sits between engineering and mathematical biology. He's at the University of Auckland in New Zealand. And Oliver is the main kind of connection with this work. So people who are on, or people who don't know Oliver, he's very active on Twitter or ex-Twitter. So you might know him online, but Oliver's the main connection with a lot of the kind of the models that I'm going to talk about today and the ideas. Okay, so I'm going to talk about an application in ecology that is relevant to where I'm speaking from today. So here is a map of Australia. We are sitting in the southern hemisphere, so north is up the page here. I am QUT, where I'm at the moment, is in Brisbane, the state capital. So Brisbane's sitting here on the map, and this is a picture of Brisbane City. My university is over here, which is a lovely place to work. So if you visit Brisbane, QUT is right in the centre of town. If you've ever visited Australia, or if you visit Australia in the future, you might see images like this out of the window of the plane. So the east coast of Australia, north of Brisbane, so towards the tropics, is home to Australia's Great Barrier Reef. It is, depending upon what definition you use, if you look at Wikipedia, it will tell you it's something like 2,500 kilometres long.
Wow.
So there's this vast population of corals that sits off the coast. So Brisbane is down here. So tropical, north is up the page. That extends right the way along the east coast of Australia. And of course, this is a very important habitat. It's a
I think there is noise from. I will unmute.
That's okay. That's okay. That's fine. So this is an important habitat for fisheries, for tourism, and an innately important ecosystem. And one of the things that we are aware of, especially living here, this is the state of Queensland, is the impact of kind of detrimental kind of ecological processes that damage the reef. So we live in the tropics, so we have tropical cyclones. Tropical cyclones can break the reef apart. We have kind of agricultural runoff from farming along the coast here, which impacts the reef, as well as a more recently, say since the 1990s, repeated bleaching events where the water, because of global warming, is unusually hot, which kills the corals. So there's a vast amount of money and effort spent in Australia upon monitoring the reef, understanding what steps can be taken to protect the reef from cyclones and from agricultural runoff and from coral bleaching. And as part of that, mathematical models play an important role. So this is the kind of data that I'm going to talk about today. It's extremely simple looking data, but within its simplicity, there's a lot of detail that is easy to overlook. So here is, on the inset here, maybe I can go to the laser pointer, map of Australia. Brisbane's in the northeast corner up here, Queensland is in the northeast corner. And at the lower end of the reef, I'm looking at data at a coral reef called Lady Musgrave Island. This is an island that you can go and visit. I've not been there, but I've been on the shore and I've seen boats going to and from Lady Musgrave Island, and there's a lot of coral growth there. So what I'm showing here on the right-hand side is some data that shows, as a function of time, the proportion of area in the reef covered by hard corals. So this is data after there's been some kind of event that has killed the corals or broken the corals. So maybe it's a cyclone, maybe it's been a coral bleaching event, but the coverage is normally somewhere up around about 70 or 80%. And there's been some event which has killed the corals or removed the corals from the system. And then the corals, the question is, do they regrow? And if they regrow, how long does it take? So this is, you can see with the data here, this is over 10 years. So it takes over 10 years for the coral system that's been damaged to regrow. And of course, if we have damaged reefs, an interesting question is, can we prioritize the reefs? Can we make a prediction early on about whether it's going to grow and how long it's going to grow? So in order to do that, one way to do that is to use a mathematical model. So as I said at the beginning, I'm going to talk about extremely simple mathematical models, but the implications of these models are very important. Let me get rid of the laser pointer.
Yeah.
Okay. So I am going to talk about, as I said, an extremely simple mathematical model that you've undoubtedly seen before. Exactly. So we're going to talk about the logistic growth model. And I must say, in this presentation, I have mixed up some figures from a couple of different papers. So I'm going to talk about the logistic growth model. I'm going to have slightly different notation in a couple of the slides, but the idea, because the idea of the logistic growth model is so straightforward, I mean, I'll point out these differences, and hopefully it should be obvious. I hope it should be obvious. So what we're talking about here is solving a mathematical model. Now, of course, it's a simple model. We can solve it with pen and paper. I teach my students how to do this in first year calculus. That doesn't mean it's simple. It probably means it's useful. And we're going to talk about the time evolution of some variable S, which I think is the total coral coverage. So it's going to be a proportion of the area covered by hard corals. And of course, the logistic growth model says that at low densities, I'm going to have some growth rate at rate lambda proportional to S. And I have this extra term here in square brackets, which tells us that as the coverage S asymptote or grows towards the carrying capacity K, that the dSdt goes to 0. So this is a standard classic textbook thing, straight out of Murray, straight out of Leah Edelstein-Cachette's book, all of the standard mathematical biology books. But what I want to talk about now is how we connect this model with some data. So if I want to solve this model, whether I do it with a computer simulation or whether I do it with a pen and paper, To solve this model, I need to specify some parameters. I need to specify the growth rate. I need to specify the carrying capacity. And I also need to specify the initial density or the initial value of S. Later on, I'm going to talk about this extra term here, sigma, which is really how we relate the model to the data. And what I've shown here underneath is a plot of the data and a solution of the model, and the solution of the model looks like it captures key features of the data. We've got seemingly exponential growth at early time, and then at later time, the density is going to asymptote towards some constant. Okay, so in order to do this, what I'm going to do in the next few slides is just to lay out, once we've got a mechanistic model, which is my logistic equation. I could have a different model, and later on I'll show you a different model, but I'm also going to have an observation model, which is going to be the connection between the data and the mathematical model. So what do I mean by this? It's some notation. I am going to collect data at different values of time. So I'm going to index it with subscript I. So I'm going to collect, I think I've got values of coral coverage at 11 values of time. So I is an index from 1 to 11. And I'm going to be given some observations from some field experiment or some experiment. And I'm going to use the subscript O. In my mind, when I see O, I think observations. So at each time, I'm going to make some observations, and in principle, I can observe multiple things. So I'm going to use the index I to represent time, and I'm going to use the index J to represent how many things I'm going to observe. In this example here, I'm going to observe one thing. So I don't really need the J, but I'm going to leave it there anyway. So I'm going to make a basic assumption, which is very, very standard assumption, which is to say that my observations, given some parameters in a model, are going to be normally distributed or distributed with a Gaussian distribution about the, there's no observation here, so I'm going to have about the solution of some mathematical model, which is going to be my prediction, and there's going to be some variability. So the data is noisy, and I'm going to characterize this variability with some measure of variance. We're going to calculate this variance from the data, and we can explain how to do that in a moment. And this is a very, very standard assumption. I'm going to come back to this and point out at the end, you don't have to make this assumption, but it's a very standard thing to do. So once I've got an observation model, so this is my normal observation model, my additive Gaussian observation model. Once I've got a mechanistic model, then in principle, I can write down a likelihood function or a log likelihood function. Well, what does this mean? What this means is I've got I observations over time. At each observation, I may have J different types of observations. For us here, for this application, J is just one. So this inner sum doesn't really play a role. And then what I can do is calculate a normal density. So I can ask myself, where about the normal distribution does my observation fit? And I've got some variance, which I haven't specified yet, but I'll explain in a moment how I calculate that variance. If I take the logarithm of the normal density, and I've got some independence assumption, essentially once I take, I could, without the log, I could take products by invoking an independence assumption, but with the logarithm here, that means I can add the terms up. So this gives me a log likelihood function, which I'm going to write down with script L, and it's a function of the parameters theta, and we're going to treat this as a function of theta for some given data. So if I'm given some data, I'm really going to think about this log likelihood L as a function of theta. Typically, theta, in our previous example, we've got 4 parameters, so we typically think of it as a multidimensional function. Could have, depending upon how many parameters we have. Okay, so then I ask myself, how, we've got the right ingredients now to connect my mathematical mechanistic model to our data. So I am going to compute the maximum value of the log likelihood function over all possible values of theta. Let's say I've got all possible values of theta given the data, and this is called the maximum likelihood estimation. I'm going to represent that with a theta hat. So out of all particular values of the growth rate, carrying capacity, initial density, and the variance, or the standard deviation, I can maximize out. I can find the value of each of these parameters that gives me the maximum likelihood. And this, in principle, gives me the best fit. Now, this is a very standard calculation to make. Maximum likelihood estimation is a very routine way to calculate parameters. And of course, these parameters tell us, or potentially tell us, about the biology. So, for example, the value of lambda is a growth rate. So if we have a particular growth rate, if we take 1 over that growth rate, it will give us an estimate of the timescale of recovery. The carrying capacity is the long-term density of corals. So that tells us, the estimate of carrying capacity will tell us how much coral will be on the reef after a long time. So the process of doing this connection can tell us about biology, can tell us about ecology. But one thing maximum likelihood estimation doesn't do at this point, it doesn't tell us what our uncertainty is or in these values of the parameters. And that's what I'm going to talk about next, which is a question about identifiability. So identifiability is a broad term. Here I'm going to talk about something called practical identifiability. And I'm going to show you some examples of problems that are both practically identifiable and practically non-identifiable. What does that mean? If something is practically identifiable, that means there is enough information in the data to give precise estimates of the parameters, which is really what we want. If there's not enough information in the data, if we haven't got much data, then we may not be able to get a precise estimate. And so what I'm going to talk about on the next slide or two is some relatively simple tools that we can use that can help us quantify the practical identifiability. So I'm going to define on this first line here, I've already got this log likelihood function, script L, and I can take the log likelihood function and I can normalize it simply by subtracting the maximum log likelihood. So the log likelihood at the value of theta hat is some number. If I just shift everything by that number, then I get a normalized log likelihood, which I put a hat on here. And the nice thing about the normalized log likelihood is the maximum value is 0. So I'm just shifting the log likelihood function.
So always negative, right?
In this case, once we've shifted it, yes, the maximum is 0. The other values, that's right. So I'll show you some plots in a moment. I'll show you some maths here, and I'll try and put the results in between the maths to kind of make it join up. So what I'm going to do, which is really to describe now the idea of taking a profile likelihood, is I'm going to take my parameter vector, theta, and I'm going to divide it into 2 components. And we've got lots of choice in how we can make this definition. And I'm going to try and point this out in a very simple way. So I'm going to define some components of theta to be our target parameter. So out of all of these parameters we've got down here, let's say I'm really interested in just lambda for whatever reason. That might come from the biology, or it might come from some intuition, but I might be interested in targeting one of the parameters. That means the complement of the parameters, K, S naught, and sigma, we call those nuisance parameters. Now, of course, within this framework, I can target any parameter, any single parameter, lambda, K, S naught, or sigma. And later on, I can show you I can target combinations of parameters. So I could target 2 parameters and forget the others. And I'm going to try and show you those options today. What I then do is to define a new function called the profile likelihood. When I say I do it, this is just me implementing this idea. It's certainly not my idea. It's a very old idea. And I give this the variable script L hat subscript P. So when I see P, I think profile. The profile likelihood is a function of the interest parameter given the data. And essentially, again, I'm going to optimize. So for a particular interest parameter that I'm interested in, I'm going to optimize out all of the others. And so what this allows us to do is to take, in principle, I'll show you an example in a moment, a complicated log likelihood function, and to really drill down inside that log likelihood function and target some of the parameters. Now, as I said before, this is a very well-established idea. When I first started learning about these ideas, my colleague Oliver told me to check out this book. This book, in all likelihood, by Poritan, is just a favorite of mine. It's got lots of theoretical background about profile likelihood in it. It's also got lots of practical implementation. So I'm not spruiking this for any reason other than it's an excellent resource. Okay, so what I'm going to do here is show you kind of a graphical idea of profile likelihood in an extremely simple case. Graphically, this case is, I'm going to show you this case in the hope that it's visually easy to interpret, but it's sufficiently simple you probably wouldn't do it in practice. So this is like an education tool. So in the top right hand here, I'm going to plot contours and regions of contours in a log likelihood function, and I've got two parameters only. So I can have parameter 1, θ1 on the horizontal axis, and parameter 2, θ2 on the vertical axis. And what I've got is some point in the middle here, the black point there, that's going to be my point of maximum likelihood. So that's going to be the point where the likelihood here, that the normalized likelihood is 0. And then as I move away from that point, the log likelihood is going to decrease. And I've colored in some particular contours. So I've shaded some contours in here because different threshold values of the log likelihood give rise to asymptotic confidence limits. And these asymptotic confidence limits are explained in Poritan's book, and they're associated with an asymptotic, meaning a lot of data, the limit of lots of data. What are the confidence intervals? So what I've got here in the left and underneath the log likelihood function are profile likelihoods. So let's just focus on this one at the bottom here. This is the profile likelihood of the parameter on the horizontal axis. I might call it θ1. And the way we calculate it is to look at fixed values of θ1. So I might take a value
μας υπενθυμίσει πώς ήταν, ναι.
Oh, wait a moment. I will unmute him. Sorry.
That's okay.
Okay. Oh, yeah. Today we are. Okay.
Yeah.
Go ahead. Yeah. It was not.
Is that a,
yeah.
Okay.
Yeah.
So we're going to compute the.
Yeah. Sorry. Please go ahead. Yeah.
Okay, that's fine. So we compute the profile likelihood by taking a fixed value of θ1 and just looking up and then looking to find the maximum, so the optimum value of the log likelihood along that line. And what that does is it collapses our two-dimensional log likelihood into a simple univariate profile. And it's very easy to look at this profile and identify the maximum. It's very easy to draw a horizontal line at some asymptotic threshold. This is a threshold that denotes a 95% confidence interval. And then that allows us to say that our most likely estimate of θ1 is this number here, 1.03, let's say, and we've got some asymptotic confidence intervals between these two values here. And of course, we can do that for θ2 as well. We can hold fixed values of θ2, move across the parameter space and find the maximum. So this is the concept of the profile likelihood. It's an optimization tool. Here we can do it visually. In general, we do it with numerical optimization, which I'll show you in a moment. So back to my application. Here is my data. I've plotted the solution of my model at the maximum likelihood estimate. And what I'd like to know is how precise are my estimates of lambda, k, and s naught. So to do that, I'm going to compute profile likelihoods of each of the parameters. So these profile likelihoods are computed using a numerical optimization. So here's a profile likelihood for lambda. I'm going to take a grid of values of lambda. I might go from 0 up to 0.005. I'm going to hold at each point across that grid, I hold lambda constant, and I optimize out the other three values numerically using NLOpt or some fmin con, some existing numerical optimization. And what I get is this very easy to interpret univariate profile log likelihood. We can see there's a well-defined peak, which tells us the MLE value, and we can take the intersection with the thresholds here to give us a confidence interval on our 95% asymptotic confidence. So this tells us not only does my MLE estimate of lambda, not only do I know what it is, but I now know what the uncertainty in that value is. And this is all done through numerical optimization. It's a very simple computation to make, and I can do it for any of the parameters. So again, univariate profile likelihood for the carrying capacity density, univariate profile likelihood for the initial density, and also for the variance. So this tells us that this mathematical model, logistic model, is identifiable, or it's practically identifiable because we've got enough data. Okay, so what I'm going to do now is just take all of those tools and talk through some what I think are very fundamental questions about model selection. And I've got as I said before, I'm slightly mixing up my notation here. If any of us goes to a mathematical biology textbook, if we go and look at Murray's book or Leah Edelstein Cachette's book, we will find that there is many choices of models that we can use. Often, if you're like me, you might not know which model to use. So I'm going to write down here what I think of as a generalized logistic term. So now my variable is going to be C. I've changed context a little bit, but the same ideas hold. I've got some growth rate R. I've got R times C. So, dc dt equals R. C gives me exponential growth. And it's really this extra factor here, F, which I call a crowding function, and other people call a crowding function. The choice of crowding function gives rise to many different options for kind of this sigmoid growth curve. So here are three very standard options that you'll find written down in many textbooks and research papers. We've already talked about the logistic growth. That's the linearly decreasing function of C, and F goes to 0 as C goes to K. Straight line. I'll show you a picture in a moment. Gompertz, the people who do the modelling on the barrier reef use the Gompertz model for reasons that I could talk about. They're a bit tangential to this talk. So the Gompertz model has a logarithmically decreasing growth function. And another model introduced in the plant biology literature is called the Richards model. The Richards model is where we have 1 minus C on K to some power. When the power is equal to 1, the Richards model is the logistic model. So let's have a look at what these models look like. Here I'm plotting the crowding function as a function of density. So C over K goes between 0 to 1. So logistic growth is a straight line joining 0, 1 to 1, 0. Gompertz here is a logarithmically decreasing function. Of course, it blows up when C is equal to 0. And Richards here depends upon this exponent beta. So I've plotted this here for values of beta equals to 1/4, 1/2, 3/4, 1, 1.5, and 2. So this purple line in here is the same as this blue line over there. So the Richards model includes the logistic model. And here are some solutions. This is a solution of the logistic equation, a solution of the Gompertz equation, and some solutions of the Richards equation for different values of beta. So these solutions down here all have the same sigmoid curve. Now, it's relatively straightforward to take the data that we looked at before and to calculate the maximum likelihood estimate and to plot the solution of the model. So here's the MLE solution of the logistic curve, the Gompertz curve, and the Richards curve. And they all match the data, at least by eye, at least to me. The match is fantastic. So if someone presses me and says, how do I choose which model? I'm not sure at this point. Maybe I prefer one over the other. The Richards equation is, perhaps you could think of it as being the most complicated model because it's got this extra parameter with this extra degree of freedom. So we might be tempted to go with this model. But what I'm going to show you in a moment is just a word of warning, perhaps not to do that. What I can do is to rank these models in terms of their identifiability.
I see.
So what I've plotted here in each column are the univariate profile likelihoods for the different models. Profile likelihoods for the logistic equation, the growth rate, the carrying capacity, the initial density, using our data. Profile likelihood for the Gompertz model, the growth rate, carrying capacity, and the initial density. Profile likelihood for the Richards model, growth rate, carrying capacity, initial density, and the exponent. And one thing we can see straight away is that the Richards model is not identifiable. We
Mhm.
cannot, within sensible bounds, we can calculate an MLE, but
Mhm.
the profile likelihood is flat. There are many choices of growth rate which match the data. So you can't trust the MLE in this instance. The exponent is also flat, relatively flat. We can't draw sensible 95% confidence intervals. Gompert suffers a similar issue in that we've got kind of a one-sided identifiability here on the initial density. It's very difficult to draw asymptotic confidence limits about this when our profile likelihood isn't sufficiently curved. We can, however, with the logistic model, see that all three parameters are identifiable. So based on this concept of identifiability, I would prefer to work with a logistic model because the data are sufficient to identify the parameters. So in terms of model selection, a straightforward outcome is I would prefer to work with a model that is identifiable with the data. And profile likelihood gives us a relatively simple, fast way to make that assessment. So the talk that I'm going to give today is really in two parts, and I'm towards the end of the first part. And I'm just going to stop for a minute with a blank screen and just ask myself some questions. Jay's very helpful introduction. He talked about different types of projects that people in my group work on. Some projects are about tumor spheroids, some projects are about cell biology, some projects are about mathematical ecology. And these projects are all connected by mathematical models and data. And indeed, it's very, very satisfying, in my view, to take a mathematical model and to fit that model to the data and to use that fitting procedure to think about parameter values which might have a meaningful a biological meaning. But one thing that I would say after many years of collaborating with cell biologists and ecologists, often they don't care about a parameter value. Often, not always, but often. If I get really excited and tell my collaborator that my growth rate is 0.0025, I might get very excited about that and say I've got some uncertainty intervals. It's potentially the case that the focus on the parameters is not the first thing that my collaborators are interested in. In my experience, they're usually interested in the solution of the model, which is the prediction. So what I'm going to do now for the next little bit is talk about the connection between parameter estimation and prediction and show you how it's relatively computationally straightforward to take a log likelihood function, profile likelihood functions, and make predictions that I think are more relevant to the people that we might try and work with. So I'm going to introduce an idea which is similar to what we've already done, about taking our parameter, theta, splitting it up into interest and nuisance parameters. So I'm going to take an interest parameter, psi, and have a nuisance parameter, omega. That can be any combination. And I'm going to use a property of the likelihood function called the invariance of the likelihood. So the picture that I showed you before about the likelihood function, the log likelihood function really told me something about how different choices of parameters relate to a match with the data. So on that plot that I showed before, the two-dimensional plot, I could pick out different values of parameters. I could calculate the log likelihood, and that gave me a way of quantifying the best fit with the data. The invariance of the likelihood is a similar idea, which says that if I've got a function of the parameters, which now I'm writing down as the variable q, that means for each for nicely behaved functions, let's assume that everything is nicely behaved, I can take the function of the parameters, and that function of the parameters also gets ranked by the log likelihood. So if I've got several choices of parameters, I can rank by the log likelihood. I can take a function of those parameters and they get the same ranking. This is called this is loosely related to something called the invariance of the likelihood. Now, I haven't said what Q is, but for us, often the function we're interested in is the solution of the mathematical model, which gives rise to a prediction. Now, it turns out this idea holds whether we think of theta in general or whether we think of taking a profile. So what do we think about? Here is a profile likelihood. As I trace over this profile likelihood here, I'm tracing a curve where I've got different values of my interest parameter psi. Along this curve here, there are also, even though I haven't shown them, values of as I optimize out to calculate the profile likelihood, there are values of the nuisance parameters along there. So I can take those values of the parameters, let's say along a mesh of the curve here, and map them forward. And what that allows me to do is to see how the predictions, that is the solution of the model, varies across this profile. And of course, for each choice of parameters, I've got a value of the log of the profile likelihood, which tells me how likely those parameters are. So this is what I'm doing in this slide here. What I'm doing is going across each univariate profile likelihood for lambda, k, and the initial value. What I'm doing is solving the mathematical model forward as I go around that profile likelihood. And that means I get a bunch of prediction curves. If I take the profile likelihoods, let me go back a slide. If I take the values only above the threshold, so this orange line here is the 95% threshold. If I only take these, then all of these predictions up here, we're going to map the 95% confidence set from parameter space into the 95% predictions from 95% confidence interval into the prediction space, thanks to the invariance of the likelihood. Now, the solution of the mathematical model doesn't depend upon sigma. Sigma was about the noise model. So I'm just going to focus on lambda, k, and s naught. And what we can see here is that for each parameter, we can relate the uncertainty in the parameter to a family of solutions, and I can form an envelope. And these family of solutions, it's interpretable. So here is the family of solutions for the carrying capacity, and we can see it's fairly narrow down here at early time, and it's fairly wide up here at late time. Now that makes sense because the carrying capacity affects the late time behavior. The initial density here is narrow, somewhere along here, but wide down here. The initial density impacts the early time behavior. So the nice thing about looking at the predictions parameter by parameter is we can interpret the uncertainty in our prediction with each of the parameters. Okay, if you want to know something, again, I'm not plugging any particular textbook here, but if you would like to know something about the invariance of the likelihood, this is a fantastic text that I often reach for. It's a really fantastic resource. Okay, one thing I can do is remember that my prediction depends not just upon three parameters separately, but it depends upon the likelihood function where they all act together. So I can take my three predictions for each of those parameters, and I can simply take their union. Taking the union of these curves is extremely straightforward computationally, of just finding the maximum over some vectors. And I can plot here in red my prediction envelope, my 95% prediction envelope. Because the model is so simple in this case here, because I'm really just dealing with a three-dimensional parameter space in terms of solving the model, what I can do is discretize the full likelihood. So I've got a three-dimensional parameter space, a cube. I can discretize it, let's say, between some limits, 100 grid points in each direction. So I can take, let's say, 100 to the power of 3 values of lambda, k, and s. I can map them forward, and any values of any predictions that are associated with values of the log likelihood within the threshold, I can make a prediction interval. These prediction intervals look similar. One's an approximation of the other. But the point I would try and make is that the union of univariate profile predictions is extremely simple. A few seconds of computation. If we're discretizing a full likelihood, even with an exact solution on my laptop here, this computation could take several minutes, maybe 10 minutes of computation. So very, very fast prediction or a slower prediction. And our experience is that as the model becomes more complicated, this speed up becomes more important.
I see.
All right, so now what I'm going to do is turn to the last point. And the last point is really just to revisit that previous point and to ask ourselves, can we do a bit better? If you look back at the previous plot, the idea here is that the red prediction interval is a cheap approximation of the blue prediction interval. I'm going to try and get a better prediction interval. And the quick answer is yes, we can do it better. The slower answer is I'm just going to step you through some details. To do that, I am going to leave the coral data behind, and I'm going to talk for the next few slides about a synthetic data study. The blue curve here is a solution of the logistic equation. The orange dots are some samples of the solution with some additive Gaussian noise. So at each point, several points along here, I take the solution of the logistic equation and I add a sample from a normal distribution with zero mean and some fixed variance. And this acts like a synthetic data study, except in this case, I know the parameter values. I know the growth rate, I know the carrying capacity, and I know the variance. I can repeat everything I've done before. I've specified the variance here. So in my parameter list down here, I'm going to leave the variance off. But I can repeat all of these calculations. I can calculate the MLE value, I can calculate univariate profiles, but I'm just going to finish up by showing you that I can also calculate profile likelihoods where the interest parameter is more than one parameter. So everything I showed you before, the interest parameter was one parameter. I can also specify the interest parameter to be pairs of parameters. So I could specify the interest parameter to be lambda and k, and then the nuisance parameter is C naught. I could specify the interest parameter as lambda and C naught, and then the nuisance parameter will be K. Or I could specify that the interest parameter is K and C naught, and then the nuisance parameter is lambda. Everything I told you about the univariate profile can then be repeated to construct what we call a bivariate profile, simply by using numerical optimization. This time, instead of taking a one-dimensional mesh of the interest parameters, we've got a two-dimensional mesh. So let's have a look at this. This slide is a bit busy, but I'll talk it through. This is the picture I showed you before. This is a logistic growth curve. I've got some sample data, and I'm plotting here the MLE solution. And we can see that the MLE, in principle, matches the data reasonably well. Then I've got three sets of results here. Let's focus on the ones on the right-hand side. I have then used numerical optimization to compute a bivariate profile likelihood where my interest parameters are the carrying capacity and the growth rate. And instead of, as I said before, instead of a one-dimensional mesh, here I've just got a two-dimensional mesh, very simple two-dimensional mesh, and I've showed the mesh points here with little crosses. I've got the MLE value plotted here as a dot in the middle, and I'm taking a threshold contour of the 95% confidence intervals. And so parameter value shown in red here, parameter values inside the confidence intervals are the parameter confidence set associated with the 95% asymptotic threshold. And of course, I can just solve the mathematical model for all parameter values sitting in here, and I can plot a family of solutions on the right-hand side there. In the family of solutions, I've got the MLE solution. I've got a bunch of grey solutions, which correspond to each little cross. And for the family of solutions, at each time point, I can construct an upper and lower limit, shown here in red. This is a profile-wise prediction for a bivariate profile. I can do the same for the other bivariates. Here's the bivariate profile for the initial density and the growth rate, mapped to a prediction interval. Here's the bivariate profile for the initial density and the carrying capacity, again mapped to the prediction interval. One thing I did here, which was good for explaining, but perhaps not computationally efficient, is I evaluated the bivariate profile likelihood on a mesh. I evaluated the function many times out here in a low profile likelihood region. Here's the same set of results again, using a very, very simple idea, which is instead of having a mesh, is to choose some points at random in the parameter space and then use bisection algorithm, so first year computational science bisection algorithm, to move these points so they lie on the threshold. So here's the threshold in K lambda, here's the threshold in C naught lambda, here's the threshold in C naught K, and this time I solve the model just on the threshold here, and then I produce a profile-wise prediction. So I'm almost finished. I know there's a lot in these slides, but I'm almost done. So here's the takeaway point. Here is a comparison of, I'm comparing here several things. My MLE solution, because I've got a simple model, I can sample the parameter space using what we call a gold standard full likelihood, using a rejection sampling idea. This is computationally expensive, but achievable in this case here. And I'm plotting the upper and lower 95% prediction limits in gold using the full likelihood. If I do what I did before and I take the union of univariate profiles, I get the red curve. And of course, it's an approximation, but it's not a great approximation in this example here. If I do everything now, but I take the union of the bivariate profile predictions, I'm kind of getting, in this case here, the best of both worlds. I don't have to sample the full likelihood, so the gold curves here are the same as the gold curves here. The MLE is the MLE, but my approximation, now that comes from bivariate profile likelihood predictions, actually is a very good approximation of the full likelihood method, as well as it gives us some insight into how groups of parameters are related to each other. So this is the question I asked, can I do better? This plot here tells me that I can. So before I take some questions, what I'm going to do is just kind of summarize what I've tried to explain today. Happy to take questions about this. This next slide is very busy, but what I'm just going to say is that we've proposed this idea of using the profile likelihood for identifiability through the univariate likelihood, through estimation, through maximum likelihood estimation, and then prediction by using bivariate profile likelihood into what we call a workflow. So workflow, as the title suggested on the talk, for identifiability, estimation, and prediction. So this slide is very busy. Happy for you to, I'll show you where to get this slide later on if you want to have a closer look at it. But the idea is we have a modeling framework. We have a mechanistic model, which could be an ODE or a PDE or something more complicated. We have a model that relates our data to, or distribution of data to our mechanistic model. Here, everything I've shown was about having a normal or additive Gaussian model. We don't necessarily have to have that, but that's the simplest one to start off with, which is often used. Within this framework, we can we can take particular realizations, like I did in the presentation, and for relatively simple models, we can use the full likelihood function to estimate parameters and to make predictions, just like I did in the example with the logistic equation. For more complicated models, we can, well, this process here can become computationally expensive very quickly for complicated models. However, even with complicated models, we can use the targeting property of the profile likelihood to construct profile likelihood-based confidence sets in parameters. We can target some parameters, small groups of parameters, single parameters, map them forward to confidence sets in data realizations. We can then combine those through taking a union to give us what can be an accurate but relatively computationally inexpensive procedure. So this is a complicated diagram. Don't think it's a good idea to try and take it all in, but I'll show you where to find it later on if it's of interest to you. So what I'll do now is just to kind of summarize what we've done and what we're doing now in the future. So what I've presented today is a workflow for identifiability, estimation, and prediction. So the identifiability we assess using the univariate profile likelihood. How curved are these univariate profile likelihoods? For a problem that is identifiable, then we use maximum likelihood estimation to give us an estimate of our best fit parameters. Given these 2 points, we can then make a prediction. So then we can propagate uncertainty in our confidence sets for parameters into uncertainty in our confidence set for predictions using the bivariate profile likelihood. And this is something that I think makes modelling more appealing to our collaborators in the life sciences. It's the prediction. One thing in the abstract and the title, I mentioned that this is efficient. This is efficient because what we're doing is using numerical optimization. So we are using established optimization routines to construct the MLE and profile likelihoods. We are not necessarily sampling. So I never mentioned MCMC. I never mentioned worrying about MCMC to converge or to warm up or all of those things here. So the efficiency comes from the fact that we are optimizing instead of sampling. Okay, there's plenty of things that you could do and that we are trying to do, but I'm just trying to capture what I haven't shown you today. This method applies to more complicated mathematical models. So by complicated, I mean partial differential equations. It applies to systems of differential equations. I would say more complicated differential equations, complicated by complicated, I mean more parameters. This idea also applies to different measurement models. Everything I've shown you today is about additive Gaussian measurement. That is because when you look at the literature in the mathematical biology space, that is what almost everybody does. Not everybody, but almost everybody. But you could use a log normal measurement model, a Poisson measurement model, or a binomial measurement model. These ideas hold across all of those generalizations. Okay, something that we're working on at the moment is that all of the models that I applied the workflow here were well identifiable. They all had well-curved univariate profiles. Ongoing work is to think about what the workflow means when the model is not well identified. Ongoing work also includes the fact that you can apply this framework to a stochastic model. Let's say a random walk model. When we spoke at the beginning of the talk, some students in the audience said they were working with stochastic models. You can connect stochastic models with this workflow using a surrogate likelihood or a synthetic likelihood. Once you've got a likelihood function that you can accept or is a good approximation, then you can run that likelihood function through this workflow. Okay, so if you want to follow up any of this work, the first results that I talked about today about the different types of logistic, Gompertz and Richards models was published last year in Journal of Theoretical Biology. Some work with a bunch of collaborators, Oliver McLaren, Ruth Baker are kind of key collaborators on this, and other people you can see here. And then some work we also did to follow this up was really to introduce the idea of prediction. And we started to introduce the idea of prediction in a piece of work down here in mathematical biosciences. Actually, that was a result of some work with some very talented undergraduate students, Shannon Walker and Emma Studeris, fantastic students to work with.
I see.
The workflow itself, and this is my last slide, the workflow itself has just been published in PLOS CB. It appeared in the September volume of PLOS CB, so you can go and have a look at that. All of the results I showed today, you can calculate those with Julia, open source Julia code if you'd like to kind of get into the weeds and explore that. And the last thing I'll talk about is we've got a review paper that is available on the archive and has just been refereed for interface. And in the review paper, what we explain is how to take these ideas and really focusing on this question of measurement error models. So what's the difference between additive Gaussian, log likelihood, a log normal or a Poisson, a binomial measurement error model? Not so much from a point of view of biology, but from a point of view of implementation. And I think the take-home message of this work is that it's not very different to change your measurement error model, and everything holds across. So Jay, that was where I was going to conclude my talk. I hope I haven't gone too far over time, but I'm very happy to take questions if people have questions.
Great, thanks so much. Wow, so I guess it was really fantastic though. So I expect there should be many questions. So yeah, please feel free to unmute yourself, and then let me